Thousands of kilometers of massive steel oil pipelines lie silently along Saudi Arabia's seabed, yet they play a crucial role in transporting the energy that sustains the global economy. Since the early expansion of the Middle East's oil industry, Saudi Arabia has built extensive offshore pipeline networks to move crude oil continuously and safely from distant offshore fields to onshore facilities in international markets. From the very beginning, installing these pipelines beneath the ocean posed enormous engineering challenges. So what compelled humanity to place thousands of kilometers of steel pipelines beneath these desert seas? The answer lies deep beneath the ocean floor, where the flow of energy begins its journey.
It's called Drill, Baby, Drill.
Drill, baby, drill. The familiar slogan often heard whenever the United States needs to boost oil production to keep its economy stable has returned once again. In reality, for decades, oil has been considered the lifeblood of the modern world. It doesn't just power cars, airplanes, and ships. It also plays a crucial role in electricity generation, plastics manufacturing, chemicals, and thousands of other industries. Even a small fluctuation in oil prices can trigger a chain reaction. Transportation costs surge, goods become more expensive, inflation rises, and the daily lives of millions of families are directly affected. To maintain this massive resource supply, workers endure long shifts on offshore drilling rigs or deep underground. The oil and gas industry is known for salaries that can exceed $100,000 per year. But in return, workers face 12 to 13-hour shifts in loud and demanding environments, spend weeks away from their families, and live with constant risks from explosions or fatal accidents. The first stage laid the groundwork for the entire project and focused on producing more than 200,000 steel oil pipeline sections, each manufactured under extremely strict accuracy and quality requirements. This represented a major logistical operation, demanding large-scale industrial production capacity and continuous inspection procedures. The pipe segments were fabricated from high-strength steel plates, carefully engineered to withstand operating pressure and harsh offshore conditions. Each section measured roughly 1,150 millimeters in outer diameter and reached lengths of up to 2 meters. The production process began by rolling flat steel plates into cylindrical forms, followed by longitudinal welding along the seam. Hydraulic expansion was then carried out to ensure precise dimensions and perfect roundness, even while the pipe ends were beveled to prepare them for offshore welding during installation. To meet the project's total material demand, 3 major pipe manufacturing plants were mobilized across Saudi Arabia. These facilities operated around the clock, maintaining an average production rate of nearly 100 oil pipeline sections per day. Every pipe segment underwent a comprehensive quality inspection process, including non-destructive testing of weld seams to guarantee structural reliability before deployment offshore. The application of protective coatings was essential to ensure long-term performance and durability. During fabrication, multiple protective layers were added to improve flow performance and preserve the strength of the pipeline over time. A low-friction epoxy lining was applied to the inner surface of each pipe, significantly reducing resistance as crude oil moved through the system and minimizing pressure losses along the extremely long offshore routes, a critical factor for maintaining efficient oil transportation. At the same time, a specialized external polymer or epoxy anti-corrosion coating was applied to the outer steel surface. This layer acted as the primary defense against electrochemical reactions and chemical corrosion caused by the aggressive seawater environment surrounding Saudi Arabia's offshore oil fields. Together, these protective systems played a decisive role in extending the operational lifespan of the Saudi Arabian oil pipelines. After fabrication and concrete weight coating were completed, the steel oil pipeline sections were transported to Saudi Arabia's coastal ports. This stage required close coordination between manufacturing plants, storage yards, and port facilities. Each pipe section, weighing several tens of tons, was loaded onto specialized transport vehicles or barges and moved to coastal transfer terminals. At the ports, the pipes were stored in large yards and arranged according to the planned installation sequence to maintain efficient material flow. Heavy cranes and handling systems were used to load, unload, and position the pipes safely, minimizing impact and reducing the risk of damage. From these facilities, the pipe sections were transferred onto supply vessels or offshore pipe-laying ships, following coordinated schedules that ensured a steady and uninterrupted supply of materials for Saudi Arabia's offshore oil pipeline installation. On specialized pipe-laying vessels operating offshore Saudi Arabia, the entire deck functions as a closed-loop industrial assembly line, where every installation step is performed continuously in the middle of the sea. The process begins when two oil pipeline sections, each weighing up to about 24 tons, are positioned for welding and carefully aligned. Automated welding systems then complete a full circular weld around the pipe, after which inspection equipment immediately scans the joint to detect defects or possible leaks. Only connections that meet strict technical standards are allowed to move forward along the line. The welded joint is then sealed using a dedicated protection system that combines heat-shrink sleeves with flexible filler materials to prevent corrosion while allowing the pipeline to adjust to uneven seabed terrain as the vessel slowly advances along the planned route. The connected pipe sections are continuously guided into the water and gradually lowered into their final position through precise coordination between transport, installation, and positioning systems. This method allows crews to install up to 3 kilometers of Saudi Arabia's offshore oil pipeline per day, a speed rarely achieved in offshore construction. The pipeline installation process also had to overcome geological and marine environmental challenges through careful seabed preparation and the management of crossing points. While many areas of the route had seabed conditions stable enough to support the Saudi Arabia oil pipeline with minimal intervention, this was not true along the entire alignment. In sections where the seabed was uneven or rocky, specialized support vessels operated ahead of installation to fill depressions with rock and gravel, creating a level and stable base for the pipeline. In shallow water zones exposed to strong waves and powerful currents, the pipeline could not simply rest on the seabed. Instead, it was installed inside pre-excavated trenches that were later backfilled to secure and protect the pipe. Beyond natural seabed conditions, the Saudi Arabia offshore oil pipeline route also intersected with existing subsea infrastructure. At locations where the pipeline crossed underwater power lines, communication cables, or other pipelines, protective rock berms were constructed to shield each system. These measures ensured the structural stability and long-term reliability of all infrastructure sharing the seabed. Beneath the Earth's crust, ancient sediment layers formed millions of years ago have preserved vast reserves of oil and natural gas, energy resources that have shaped modern civilization. However, most of these oil fields are not located beneath human settlements but lie hidden thousands of meters below the ocean floor. To reach them, humanity had to create massive machines known as offshore oil rigs. The construction of an oil city in the middle of the ocean begins on land, where gigantic steel structures weighing tens of thousands of tons are manufactured in shipyards before being transported offshore by specialized heavy-lift vessels. Once at the extraction site, fixed platforms are lowered into position, and enormous steel legs are driven deep into the seabed and reinforced with concrete, making them stable enough to operate in water depths ranging from 60 to 120 meters. In more remote offshore regions, where the ocean covers depths of several thousand meters, engineers rely on semi-submersible drilling rigs. These structures remain stable thanks to massive floating pontoons positioned beneath the water's surface and anchoring systems made of chains stretching for thousands of meters, allowing safe operations at depths of up to 12,000 feet, roughly 12 times the height of the Eiffel Tower. Just above the seabed, a specialized system known as a subsea wellhead is installed, functioning like a giant valve that controls the flow of oil and natural gas. Positioned only a few meters above the ocean floor, this equipment must withstand pressures hundreds of times greater than those experienced on land. Installation requires near-perfect precision, with tolerances measured in mere inches, and is carried out using ROVs, remotely operated vehicles that work in the complete darkness of the deep ocean. Robotic arms carefully maneuver multi-ton steel components, connecting, sealing, and securing the pipeline system. From the wellhead, oil and natural gas flow into a vast network of subsea pipelines stretching for dozens of kilometers across the seabed. These pipelines are protected by multiple anti-corrosion layers, and welded section by section and continuously monitored to prevent leaks, since even a small crack could trigger a serious environmental disaster. Rising above the waves are floating fortresses known as FPSOs, floating production, storage, and offloading vessels. Unlike fixed platforms, FPSOs are not permanently attached to the seabed. Instead, they are held in position by massive steel mooring chains, allowing the vessel to move with ocean swells while maintaining stable connections to the extraction systems below. A single FPSO can store up to 2 million barrels of oil, serving both as an initial processing facility for crude oil and as a floating storage unit before the oil is transferred to long-distance tanker ships. From fixed platforms and semi-submersible rigs to subsea wellheads, vast underwater pipeline networks, and gigantic FPSOs, all these elements form a continuous extraction chain stretching from deep beneath the earth to the ocean surface, transforming energy buried for millions of years into the fuel that powers the modern world. The journey of oil and gas extraction begins with offshore exploration. On the deck of survey vessels, engineers lower massive acoustic transmitters into the sea. The sound waves travel down to the seabed, bounce back, and are captured by a network of sensors on the surface. From this data, a three-dimensional seismic map is constructed revealing the sedimentary layers that may have trapped oil and gas for millions of years. But maps alone cannot provide certainty. A drilling platform is positioned at the selected location, where hundreds of steel pipes about 9 meters in length are linked together one after another, creating a massive drilling assembly that cuts through the ocean water and continues deep into underground rock formations. At its end sits a drill bit fitted with super hard alloy cutters, breaking the rock through continuous rotation. After the drill reaches a target depth, engineers send a monitoring device down the well, a logging instrument fitted with several sensing systems. Deep beneath the seabed, hidden in complete darkness, the logging tool releases electrical signals, sound waves, and gamma radiation that pass through the surrounding rock layers. The returning signals travel back to the surface, appearing as streams of data that show rock porosity, fluid flow capacity, and reservoir pressure. These measurements ultimately decide whether a well, costing between $50 and $100 million, will turn into a productive oil field or end as a dry well permanently abandoned. But with it comes constant risk. If drilling operations are poorly managed, reservoir pressure can suddenly surge upward, triggering a blowout. Crude oil escaping from the seabed can devastate marine ecosystems and cause environmental disasters that cost billions of dollars to contain and clean up. That is why every stage of the process must be strictly controlled, because even the smallest mistake can turn an ambitious project into a global catastrophe. But with it comes constant risk. If drilling operations are poorly managed, reservoir pressure can suddenly surge upward, triggering a blowout. Crude oil escaping from the seabed can devastate marine ecosystems and cause environmental disasters that cost billions of dollars to contain and clean up. That is why every stage of the process must be strictly controlled, because even the smallest mistake can turn an ambitious project into a global catastrophe. Once the well is secured, extraction can begin. At first, natural underground pressure pushes oil and gas upward through the production tubing. Over time, however, reservoir pressure declines, making artificial lift systems necessary, such as electric submersible pumps capable of producing up to 20,000 barrels per day, or gas lift injection used to maintain a stable flow. What reaches the surface is not pure oil, but a mixture of crude oil, gas, water, and fine sand. At the production site, this stream passes through multi-stage separators. Gas is compressed for export or re-injected into the reservoir to help sustain pressure, while water is treated to remove oil and solids before being discharged back into the sea under strict environmental regulations. The crude oil then undergoes additional processing to remove salts and impurities before being transferred into temporary storage tanks. Throughout the process, Thousands of sensors continuously monitor pressure, temperature, and flow rates at every stage. Some modern offshore platforms even transmit real-time data via satellite to onshore control centers, allowing remote intervention whenever irregularities are detected. If issues such as sudden pressure drops or abnormal flow conditions occur, automated systems can trigger alarms and even shut down the well to prevent accidents. Offshore oil production therefore operates as a tightly connected chain, from flow management and phase separation to treatment, temporary storage, and preparation for transport. It is a stage that requires extreme precision because even a minor error can result in losses worth millions of dollars and cause serious damage to the marine environment. After crude oil is initially treated and stored, the next stage is transportation to shore. In fields located closer to land, subsea pipelines stretching for dozens of kilometers carry the oil directly to refineries. In deeper offshore fields farther from the coast, crude oil is transferred onto specialized tanker ships or floating storage units, each capable of transporting millions of barrels. From there, this energy resource formed over millions of years begins its journey toward refineries and ultimately into everyday human life. So, you've learned the entire process of installing oil pipelines and oil rigs. Thank you for watching. Remember to subscribe to the channel to follow the next content.